of Z and T. That's a KVL around the loop. The voltage here is equal to voltage here plus voltage there. Right? So here it is. You can see it there. In the frequency domain, that will be simply will be R times I plus j omega L times I, plus obviously V of Z plus delta. So I write this equation, and I have it backwards, I'm sorry. Voltage here is equal to this plus that. V of Z plus delta Z. Voltage here is equal to something on the side. So that's your KVL written around the loop, and the KVL in the time domain. Likewise, we can write the node equation for here. This node equation, this current is equal to this current plus that current, right? So the sum of the currents, and that is expressed right here. I of Z plus delta Z of T is equal to I of Z of T plus delta I of Z. So you have the two KCL and KVL, both of them are written. If you combine these together, you end up with a second order differential equation. We'll see it down. Yes. Since you have access to these nodes, you don't need to copy anything, but if you'd like in the future, you can print them out and bring a copy with you here so you can take notes on top of that. Eventually, you end up with this equation 11. Equation 11 here is your second order differential equation that relates or combines the two KVL and KCL together. And you can see it here in the time domain, and you can see it there in the frequency domain. As you can see, the equation, the frequency domain, look at this, right? Look at this one. A simple linear equation that is much simpler than that obtained in time domain. And that's the whole point about using the harmonic domain for the frequency domain or the phasor domain. The convenience of the mathematics is there. And actually, if you were to take this one here, after you develop the time domain and you do the transformation, you end up the same thing. So here, the reason we're able to write it from the beginning is we learn through practice how to start the problem from the middle rather than start it from the beginning. Typically, when we started early on, we learned the time domain and we learned how to switch that way. But later on, we learned how to come this way directly from first principles. So to solve the equation in 214 here, we eventually end up using the Laplace transformation. And if you use the Laplace transformation, you end up with something similar to that, except instead of having j omega, you'll end up with s. And like we mentioned on Monday, the difference between s and j omega is the presence of the alpha term, which allows you, is it sigma? Sigma here, right? Call it sigma, I'm sorry. It is the presence of the sigma term which allows us to look at the transient part. If you drop the sigma, you are in the frequency domain and you are only looking at the steady state solution. Right? Sigma's gone, steady state only. The S gives you the full transient solution because you look at the poles and zeros and what happens from t is equal to 0 and 1. I'm doing a review, all right, supposedly. So if you feel like I'm going too fast or something is missing, please let me know. Am I going too fast? Are we all following? All right. Silence is an approval sign. And you pay the price. So speak up if you don't like it. All right, so based on that, I end up with the Laplace domain equation, which is similar to the frequency domain equation. you can see the similarity here, right? Second derivative of V of Z and S, second derivative of V of Z and J omega, R plus SL, R plus J omega L, G plus SC, G plus J omega C, V, B, right? So basically, we define this term here as gamma squared, the product here, that's a gamma squared. Okay. Later on, we will recognize that as, anyone remember what gamma was? Propagation constant, right? Complex propagation constant. Obviously here, we'll not call it complex, right? It's beyond complex. So gamma squared is R plus J omega L and all that. So this equation simplifies into this form. The second derivative of V is equal to gamma squared times V, right? And the solution for this differential equation, as we all know, basically, we recognize a class of functions, all right, that if you differentiate twice, you come up with the same exact thing, right? So what kind of a function here that when you differentiate twice, there was a constant times the same function, that's the exponential. And since the exponential will have the square root of this gamma squared, that means either a plus gamma or minus gamma, that means you have two possible solutions. And the rule is, if you have more than one possible solution in your differential equation, the general solution is a linear combination of the two. Right? So we throw both solutions in the mix and let the boundary condition decide which solution is good. The boundary condition may tell us both are good. Take 5 of this and take 20 of that. Right? So the boundary conditions will tell us how much of the e to the minus solution exists and how much of e to the plus solution will exist. So the v plus and v minus are two arbitrary quantities that we put in our solution here as coefficients of mix between the two possible solutions. And we let one condition decide how much v plus, how much v minus. And remember what the boundary conditions were. Source and equation. These were the boundary conditions that will eventually come to at some point will tell us how much of v plus and v minus. But for now, both of them exist. Likewise, here, except for gamma now, is the square root of this R plus SL times G plus SC. Now, we continue our solution to get the current because we got the voltage from solving that differential equation. So we go back up, find how the current is related to the voltage, and we get the current. And we discover the current is equal to this, and from there we come up with this solution for the current. Again, e to the minus solution, e to the plus solution, and the coefficient here, right, is multiplied by this quantity here. So we have a solution to the differential equation. We stop here because we need to examine the solution. We need to examine what gamma is, the physical meaning of gamma, and the physical meaning of the e to the minus solution and e to the plus solution, and how we can make sense out of that. Any questions before we go? All right, thank you very much. If you read ahead,